We're starting section 14.5, directional derivatives and gradients. First, we discussed the directional derivatives, then we discussed the gradient vector, then gradients and level sets and how they are related. So what we know from past section, we know about partial derivatives, and so let z be the function of x and y, f of x and y, and let a and b be a point in the domain of f. So let's say f, the graph of f is the blue, and the domain is that's a part of x and y plane. F sub x of a and b, or partial of f with respect to x, is the rate of change in the x direction or I direction at a and b. F sub y of a and b, or partial of f with respect to y, is the rate of change in the y direction or j direction at a and b. Now, so this was something we learned before, but what if we're not thinking about x direction or y direction? What if we're thinking about some just random direction? So what do we do then? Let's see, what is a random direction? We're thinking about a line or a vector in the domain. So in the domain that starts at a and b. So let's see, what's the equation of a line? Equation of a line is if you have a point and you have a direction, so let's say point P, and you have direction U, then the equation of line would be P plus T times U. So x equal to a plus pt, and y equal to b plus qt. And then, so if the domain is a straight line, I may want to use my calculus of one variable information to actually find a derivative. Now, from our calculus of one variable information, we know that the derivative along a line, if the input is on a straight line or an interval, basically the derivative is going to be the limit of the average rate of change as the two points on the line approaching, one point approaches the other. So I can write, see, we parameterize the line, therefore the f of r sub p plus t times unit vector u is going to be the function at the second line, and then minus f of p is the function at the point that we're basically finding the derivative. And so then write it back with the parameterization, and so you get limit as t approaches 0 of f of a plus pt and b plus qt minus f of a and b over t. Now we call this the directional derivative. If the function has a derivative, we call this the directional derivative of f in the direction u. For example, d sub I of f of a and b, or partial respect to in direction I, the directional derivative in direction I is equal to the partial with respect to x of a and b. And then directional derivative in direction j of f at a and b is going to be equal to f sub y of a and b, or a partial with respect to y of f at a and b. directional derivatives, the directional derivative d sub derivative with respect to in direction u of f of a and b is a scalar that measures the instantaneous rate of change, namely change in the value of f of x and y when horizontal distance traveled in direction over the horizontal distance traveled in direction u. So if you look at the u down here, there is that, and then the magenta, that is the directional, it's the basically the tangent line in the direction u. Directional derivative actually in the